Okay, so last lecture we looked at a lemma which proved that the ring of integers in a finite extension of QP. So, in the local case the ring of integer is generated by one basis. What that means is, let me remind you what that means. So, recall from last time we proved that O capital P is O sub small p of alpha for some alpha in OP. Right. So, this result need not be true in number fields. So, for warning, OK or maybe what we are using OL need not be of the form OK alpha for any alpha. Okay. So, so it is of course very beneficial when one element generates the bigger ring, and in the next proposition we are going to need this. So, let me write that next theorem. Let alpha let L over K be a finite extension, be an extension of number fields we want a formula to compute the different. Okay. Let S be set of all alpha in L such that, or let me directly write OL here, such that K alpha is equal to L. So, although the ring of integers is not generated by one element, the field, number field is always generated by one element, that is primitive element theorem. So, I take all elements in OL such that powers of those elements forms a basis of or generates L over K, and so you can find a basis in that. Okay. Let phi alpha x be the minimal polynomial of alpha in S over K. So, of course, each element of in S is algebraic over K. We can find a minimal polynomial of each of those. Okay. Then the different of L over K is the ideal generated by phi prime alpha evaluated at alpha such that alpha is in S. Okay. So, you take all these minimal polynomials of each alpha, you take its each derivative of each of them, and you evaluate that derivative at alpha. Okay. So, you get this huge sequence of numbers, and you take the ideal in OL generated by this, and then the claim is that this ideal is exactly equal to the different. Okay. All right. So, we are going to prove this now. So, first assume that OL is OK alpha for some alpha in OL. Okay. So, this is a simplifying assumption, and we have to remove this assumption of course, but we can first assume this, right. Okay. So, what I can do is I can consider phi alpha x divided by x minus alpha, right. X minus alpha will always divide this polynomial. So, I can consider this, and this will be of the form beta 0 x to the n minus 1 beta 1 x to the n minus 2 and so on up to beta n minus 1 for some beta i's in OL. Although the original polynomial phi alpha x is in OK, when you divide by x minus alpha, the resulting polynomial will not be in OK, right? It will only be in OL in general, and it will also be monic. So you have these conditions. Okay. Then let alpha okay, let me write it like this. Let alpha 0 equal to alpha 1 and so on up to alpha n minus 1 be the roots of phi alpha x equal to 0. Of course, these roots need not be in L either. They, in general, they will be in an algebraic closure of K. So, but we don't worry about that technicality so much. So, what you have is the following claim. Let me write it as a claim. Summation I going from 0 to n minus 1 phi x. So, phi alpha x by x minus alpha I into alpha I to the power j by alpha prime of alpha I. This is equal to x to the j for all j between 0 and n minus 1. Okay, so for any, so I am fixing some j. Now you see the left hand side is some complicated polynomial, the right hand side is this simple monomial x to the j, and my claim is that the complicated expression on the left hand side, it simplifies to just give you this monomial. Okay. So this complicated looking fractions and their linear combinations, it gives you this x to the j. How do you prove that two polynomials are equal? Right? How do you prove that two polynomials are equal? Well, one way to show do that would be to take their difference and show that it has more zeros than the degree of the polynomial. Okay. So that would be one way of showing it, and that is precisely what we do. So you see that degree of the polynomial on LHS left hand side is n, and degree of x to the j is equal to j, which is less than or equal to n minus 1. Hence, the two sides, hence the claim will follow if the two sides agree on at least n, no sorry, the degree of the left hand side is n minus 1, sorry, that should be, because I am taking this ratio phi alpha x by x minus alpha I, and so if they agree on n points, okay, and you see that summation I going from 0 to n minus 1, this by alpha L divided by alpha L minus alpha I. Let me kind of clarify what this means. There is, I am not dividing by 0 anywhere. So, so you see that although it looks like when L is equal to I or when I is equal to L, it seems I am dividing by 0, but that is not what I am doing. I am just evaluating this polynomial, the ratio at alpha L, and what this becomes is exactly this becomes, so this thing is 0 except for when I is equal to L. So you get, sorry, this should be L, phi alpha prime alpha L divided by, okay, maybe I'll put it in the other place. Yeah, I is equal to L, and so phi, here I should keep alpha I. Alpha L, because I is equal to L is the only relevant case, and so this is alpha L to the j, and hence the claim follows. Okay. This is a useful trick that that you should keep in mind, and it will be useful in many places, not just in number theory, by the way. All right. And so what we have is the following. So what have we proved? So recall the claim. So summation I going from 0 to n minus 1 phi alpha x by x minus alpha I times alpha I to the j divided by phi prime alpha of alpha j is, sorry, not alpha j, alpha I this is equal to x to the j. So if you equate the coefficient, now the left hand side is some complicated polynomial, but we know that it simplifies to x to the j. So equating the coefficients of x to the I don't know how to call it, x to the I for 0 less than or equal to I less than or equal to n minus 1 on both sides, we get trace from L to K of alpha to the power j beta n minus 1 minus I divided by phi alpha prime of alpha. This is equal to 1 if I is equal to j, and it's 0 if I is not equal to j. Right? So that's the right. I mean the only non-zero coefficient on the right hand side is of x to the j, and that is when that is precisely when the coefficient here, right. So anyway, what this tells you is the following. Okay. So therefore this quantity beta n minus 1 minus I by phi prime alpha by alpha such that 0 is less than or equal to I is less than or equal to n minus 1 is linearly independent over k. Not only that, it also shows you that it is dual basis of the basis 1 alpha and so on up to alpha to the n minus 1. Okay. We know that this is a basis of L over k, and then the this beta n minus 1 minus I by phi prime of alpha is a linear is a dual basis. Okay. All right. What this means is the following. So hence beta belongs to the different inverse if and only if beta is in the OK span of this dual basis beta n minus 1 minus I by phi prime alpha of alpha. Okay. All right. So this means that, so hence okay, hence we have that L over K inverse, this is generated by phi prime alpha of alpha inverse. Okay. All right. Hence this should be K, L over K, this is phi prime alpha of alpha. So at least in this special case we have what we want. Okay, so this proves the special case. So this proves the special case OL is equal to OK alpha. All right. So now we want to go to the general case, and what we are going to do is we are going to use two things. We are going to use the result that I recalled at the beginning of the lecture, that locally the ring of integers is generated by one element, and we are going to use the result that local the product of local difference is global different. Okay, that we proved a little bit a few lectures ago. Okay, so let P be a prime non-zero ideal of OK, and P contained in OL be above small p. Then there exists alpha in O capital P such that O capital P is O small p of alpha. So maybe this is let me give it as an exercise. This just requires you to go over the proof of this result that I recalled at the beginning of the lecture, that such an alpha exists. And so what you can show is that alpha does not belong to P, and alpha belongs to Pi for every Pi above P such that Pi is not equal to P. Okay. So you just have to go over the proof of the result that we had, and this is what you would get out of it. Okay. All right. So we can do the following then. So let phi I of x be the minimal polynomial of alpha, but I consider alpha as an element of Pi over O sub small p. Right. So I can do this always, and so what I get then is the following, that the constant term, so there is a little bit of checking in each of the sentence claims that I am making. The constant term of phi I of x is divisible by is in Pi. Okay, and so this is simply because, I mean, why does this happen, as phi I of alpha is equal to 0, and then you see this will be something of the form alpha to the k plus a k minus 1, alpha to the k minus 1, and so on up to a 0, and each of this is in Pi, right, and this is 0, hence so this implies that a 0, hence a 0 is in Pi. Right. So that is what I am saying, that every claim I am making requires a small argument, but it is not difficult. But AI, A0 is in OP, right, O small p, hence A0 is actually in P because it is divisible by Pi. Okay. But it is an irreducible polynomial. Phi I of x is irreducible over O small p, and so again, you know, this requires a little bit of argument. So Hensel's lemma implies that each coefficient except the leading one, coefficient is in small p. Okay. So what this means is that that if I evaluate phi I prime of alpha, then this is not divisible by our fixed capital P, right. So again, you just look at the derivative of this and you know that each coefficient is divisible by small p except the leading one, and the leading term is simply n minus 1 to the power alpha to the n minus, so n into alpha to the n minus 1, right, and so that is not divisible by p. So what this means is, therefore the power of p dividing phi prime alpha of alpha and phi I prime of alpha are the same, sorry, is the same, it is the same power, is the same, right. But we know from the easy case, but the local different LP over KP, this is generated by phi I prime of alpha, right, and that is precisely what we want, and the global different is product over all the local difference, right. Okay, and so therefore we get that this is equal to phi prime alpha of alpha such that alpha is in S. All right. So yeah, this slide. Yeah, I think, yeah, I got this indexing wrong. Let me just write this as phi prime of alpha, and I will tell you what this phi prime of alpha is. Phi of x is the minimal polynomial of alpha, but considered as an element of OP over O small p, and so this should also be phi prime of alpha. Yeah, now it's all correct. Okay, all right. So, so now we have proved a theoretical result which says that if you want to compute the different, then the way to do it is take all algebraic integers whose powers span the field and look at their minimal polynomials, look at their derivatives and evaluate them at the respective element and take the ideal generated by those. So, that gives you the different. Okay. So, although it looks like it is a way of finding the different, it is not clear if this can be turned into an algorithm, because a priori you have to take infinitely many elements. Nevertheless, we will see that this has some theoretical applications, and so in the next lecture we are going to apply this to get some more information about different, and that will help us prove that a prime is ramified if and only if it divides the different. Okay. Thank you.